Next up, we want to get a handle on the globe and get an idea of how we can make measurements and refer to where we are on that globe. So the objectives are, I get some of the main concepts of geodesy: coordinate systems, datums, ellipsoids, and geoids. And we want to take a look at map projections and the coordinate systems or coordinate reference systems that we use in GIS. Main questions are, what's the shape of the Earth and where are things on the Earth? So our goal is that we've got all these points and we want to be able to describe very precisely as possible where is A and B. So in a Cartesian coordinates, we have a right angle and a two-dimensional system. So we've got X and Y, and these are projected coordinates. So we're going to take the round Earth or spherical Earth and project it down onto something that's flat. And three-dimensional, we talk about geocentric coordinates. So now we're at the center of the Earth, and we're going to talk about X, Y, and Z. So for that opportunity, spherical coordinates make sense. Greenwich meridian here is defined as the 0. Longitude from plus 90 to, or latitude, excuse me, from plus 90 to minus 90. And the longitudes headed to the west as negative numbers and to the east as positive numbers. These values here every 22.5 degrees, called meridians, and every 22.5 degrees as a slice this way as parallels. It's important to recognize that the meridian is still a circular thing. It goes from pole to pole, but yet the parallels are slices. So they are, this is a much smaller circle down here. Sliced this way, where the meridians are all essentially roughly the same size. Okay, so geodesy is the science of measuring the size and shape. And when we do this, we need to measure from a reference surface. We could go all the way to the center of the Earth, but what we use is a concept called a datum, which is a reference surface. So we want to measure from that reference surface to determine heights. And this is important because height as we know it really isn't from, or the effect of it is not really from the center of the Earth, but it is from this surface that has a consistent characteristic, which we'll see shortly. So vertical datums would be heights above or below a surface, and horizontal would be coordinate positions on that surface. We have geocentric datums based on the ellipsoid, the center of the Earth's center of mass, and geodetic datums, which are vertical datums, basis for calculations above and below the Earth's surface. Okay, so there's many datums. Different nations may agree on points as surfaces for standards, but we need to measure the size and shape and location of these points on the surface. Okay, a little ancient history back in the BC time. It was postulated by, I can't pronounce his name, Eratosthenes. He deduced by looking at the angle of a post at Alexandria here, calculating this angle, that would be the, since there was no shadow here. So he looked at the shadow here versus the shadow there at high noon and deduced that there was these posts he knew were 805 kilometers apart, and he could measure this angle, and therefore came to the calculation that this angle was 1/50th of a circle, and so therefore this distance was 1/50th of the Earth's circumference, and so established the circumference of the globe at that point. Okay, so it's pretty complicated because the Earth isn't round. The continents are actually moving and the poles wander around. So we have a dynamic scenario for measuring the Earth. Newton suggested that since the Earth was spinning round and round, that centrifugal force would be pushing out at the equator, and so really that the Earth wouldn't be round, it would be somewhat flattened into an ellipse, and a spherical ellipse that we call an ellipsoid. So the thought was that there would be a different radius for the axis, the semi-major axis, and the semi-minor axis, so that there would be two different axes, which are shown here. So the semi-major would be along for the equator, and semi-minor would be through the poles. And how much is it flattened would be this ratio of the difference over the equator. So it turns out that no one could agree on the right size. Different countries came up with different standard ellipsoids. And the reason is because the Earth is not an ellipsoid. And so different countries would have values of R1 and R2 that would work better for their particular country. So that's what they wanted to use. But since it's not an ellipsoid, it turns out that there are other variations. The Earth's shape is a geoid. So if you take an ellipsoid, which would have a nice smooth shape, the geoid wanders around from above and below this particular shape. So the reference surface that we really need to measure everything from is this geoid, which would vary depending on where you were on the globe. So if you were over on this portion of the globe, for example, you would want an ellipsoid with a bigger radius so that this would better fit. So that's why they were the discussions of which ellipsoid was best, is because this ellipsoid might work pretty well for a country that's in here, but it's not going to work very well for a country that's over here. If we exaggerate this and we look at what the geoid looks like, you can see that this is color-coded. These would be higher sections of the geoid and lower sections of the geoid, and the continents have been superpositioned on there. And there is somewhat rhyme and reason to this, but there's also a lot of areas where it doesn't make too much sense. That's what we're up to. We now need to get a very accurate representation of this geoid shape for the entire globe.